right. Hi everyone. Once again, we want to do our fifth lecture, and in our fourth lecture, we took a voyage to understand the storm force and how it influenced the property of matter, and we realized that storm force carried by gluon is able to change color property of matter. Now, today we want to look at another force that is equivalently of obvious importance, and that is weak force. And as we discussed in the previous lecture, we realized that the hadrons is composed of the two upward quark for the and one downward quark for the proton, and one upward quark and two downward quarks for the neutrons. So while looking into this, we said also that what binds the nuclear together is because of fundamental property of the upward and downward quarks, and we also reiterated that the higher the distance, or if the farther these upward and downward quarks are, the stronger the force of attraction, and the closer they are. When they're so close, then they experience some bit of repulsive force. Now, it is important also to understand that these quarks also they experience a weak force. Then it means that if they are attached, when these quarks are attached to a weak force carried by W, then there is a certain property of this matter that is being affected. And that is the voyage that we are taking in our lecture 5, and that is our weak force. Now, if we take a look at our diagram there, then we're able to see we have the upward quark, then we have the downward quark. We have one upward quark and two downward quarks. And from the knowledge, for those who have attended my previous lectures, are able to identify this as the neutron. Because we see that the neutrons are having two downward quarks and one upward quark. Now, as you can see, when it is attached to a charge carrier, weak charge carrier, W, then this weak charge carrier is able to turn this proton or turn this downward quark into upward quark with the release of an electron. And when that one happens, then it means it shall have changed this neutron into proton. And when that one happens, it is accompanied by the beta negative decay. Now, by the way of weak force, we are able to change the neutrons to proton, and gives us a decay called beta negative decay. Now, weak force, unlike strong force, it acts over a very short distance. It doesn't act over a long distance. And the force carrier here, we must also get to know that the force carrier in the weak force is W, whereas the force carrier in the strong force is our gluon. Now, this type of force is useful in the nuclear medicine, and I think we'll exhaust much into it when we get into that module, because particularly as we will be trying to look at types of decay where we have beta positive, beta negative decay, then we'll be able to dig deep and understand how weak force is able to change or stabilize. I said by that the weak force is able to stabilize an unstable element, because when it releases beta particle, we understand that most of elements that are going decay are unstable elements unless they are small elements are added together. But under normal circumstance, most of the elements that undergo decay are unstable elements. So it means that the weak force is able to stabilize an element by so releasing an electron. Now, how do we realize instability of an element? Now, chemically, we look at the number, the valence number of an electron. But now when it comes to the nuclear aspect, we try to check into the proton-neutron ratio. If the proton-neutron ratio is not coherent to the expectation, then we expect such kind of elements to undergo decay. And when they undergo decay, they are accompanied by the production of some particles. Either it will be an alpha particle or beta negative or positive particle, and will be accompanied by the loss of energy, and this loss of energy comes in form of gamma. And this application is very important, particularly both in the treatment, in the oncology centers, and even imaging, because the energy that is being released here, the gamma energy that is being released here, or gamma radiation that is being released here, is having high penetration point. It possesses high energy, and that energy can either be used for treatment, particularly to the prostate. We can use prostate treatment. We use gamma, where we plant seeds into the prostate gland, or it can be used in imaging through the help of gamma cameras. Now, it means that as much as we are looking into the strong force of attraction, it's also important to dig deep to understand some factors that are contributed as a result of the weak force within the spheres of the particle. Now, so far we have discussed particles. We have talked of how particles being subdivided. We have mentioned the fermions, we have mentioned the bosons, we have mentioned the gluon, the weak carrier, we have mentioned the hadrons. We have been able to identify gluon, the hadrons, and to differentiate within the hadrons to know which one is the proton and which one is the neutron. Now, at this point now, it's like we are now moving out of the basic atomic structure within the sphere of our radiology physics course. Now we are moving towards, we have moved from the subatomic particles. We have discussed the strong force, we have discussed the weak force. Now we are going to discuss the electromagnetic force, because we said that electromagnetic force is a force that acts within the nuclear or within the atom. Once we are done with this, then we shall have completed our first section of this model, and then automatically we shall be welcomed into the X-ray physics, where we are now going to talk deep into how X-ray is being produced and how it's accelerated, and even how we are able to produce images through the help of the X-ray, which is a contribution of an atom. Now, we'll stop our lecture at that point. Let us meet in the next lecture, where we are going to talk about the electromagnetic force. Thank you and have a nice time. See you in the next lecture.